I'm not done with them because 6% of the tests had missing stuff on it. 6% of a full class period is 2.8 minutes. The class period yesterday was 41 minutes. Test was written to be finished within 30. This is the last time I'm going to allow 6 minutes tomorrow. That's it, done, go to the, we're going to continue. If you're done, if you're not done, whatever. You got 6 minutes. That's the way I set it out. Ladies, one of the things that was kind of disappointing to me with the test part, you guys don't trust yourselves. This is an honors level course. The pace and the rigor at which that we're working, you got to trust your skills, guys. You got to trust that you know what you're doing. You got to trust the fact that you know how to set it up and you know your steps to go through it. A lot of you guys tend to overanalyze and overthink, and that's what's lagging you and slowing you down. When you get to the high stakes tests versus ACT, SAT, and those things of that nature, you have 60 minutes and 60 questions. You got to get them done. You can't overanalyze, you can't overthink. I thought we discussed about something like this the last time around too, where we ran a little tight. But a lot of you guys were done. A lot of you guys were checking your answers, and I think also a lot of you guys were at the point where you were kind of going, I don't want to be the first one to hand it in. Trust me, I see that a lot where you guys are kind of looking around and going, who's going to be the first one up? And as soon as the first person's up, the floodgates open, okay? Don't lie, you know that you're probably one of those people that waits and doesn't want to be the first. It's okay, all right? Just remember, okay? It's not that big of a deal. So I'll give you 6 minutes tomorrow. Okay? Chapter 6. Chapter 6, we will finish up and be done with the day before Thanksgiving break. You can already plan for your test to be that Tuesday. There are 8 sections, I believe, in Chapter 6. I have completely uploaded all the PDF files for everything on the website. Everything's ready to roll. What we're going to do today is kind of talk a little bit about 6.1, and I've already written out basically all the notes you need to know in 6.1. It's all right here. It's right there in your book on page 323. It's some rules with exponents. It's how you simplify statements. We'll look at a little bit of those today, and then only take maybe 5-6 minutes to go over a couple of examples, and then we'll start in 6.2. 6.2 tends to be something a little bit newer to you. I'm going to introduce you guys into something called synthetic substitution. It is an extremely efficient way to use, instead of the old-fashioned plug and chug, if you will, it's a very efficient way to do that. We use synthetic substitution a lot in this chapter, just about every single section. And once you do maybe 2 of them, all of a sudden you're like, man, is this easy. So it just looks weird at first. Also, we're going to introduce you guys to something called end behavior when it looks at stuff on graphs. So we need to use our calculators, table functions, and going through some exponent rules. Now, when you're dealing with exponent rules, you guys have all seen these. Exponent rules are something that that you tend to forget a little bit about. What I have written up in here on the boards in the back and on the front here, and I'll leave up here for someone to go to the example stuff. Remember that A value is the base, the M or the N is the exponent. So as long as you have the same base, different exponents, and you're multiplying together, that's when you add your exponents. If you have the same base in your exponent and you're raising it to another power, that's when you multiply, and so on and so forth. Usually what happens with most students when we get into a little bit of the messy stuff is when it deals with negative exponents. And the way that I always try to remind people of is that if you're a negative person, you're not happy. You're not happy with where you are you, if you're negative? So you move. So if you think about it, if you're negative in a numerator, you're not happy there, are you? So you move to the denominator. And now you're happy. If you're negative in the denominator, you're not happy. So you move, and you go to the numerator, and then you are happy. It's the dumbest, cheesiest way to remember it, but that's where most people remember. Also, one thing that people forget, anything to the 0 power is always 1. No matter what it is, if it's raised to the 0 power, it's going to be 1. Okay? Let me show you a couple examples. I'll leave those up on the board and kind of walk you through how these things work out. When you're working with simplifying expressions like this, and you're working with exponent rules, one of the things that we always take care of first is we always take care of our numbers. We take care of numbers first, and then we go variable by variable. What I mean by taking care of our numbers is that we look and see if we can simplify the fraction. In our first example, we have 5 over 2. Can I simplify that? No. So when I go to start writing this stuff out, I go ahead and just write, well, 5 over 2. And now I start working with my exponents and my variables. The first variable I come across is x. Well, I have x squared in the numerator and x to the negative 1 in the denominator. X to the negative 1 in the denominator is not happy, is it? Where should it go? Numerator. So for this first example, I'm going to write it out in long form. And then I have y and y cubed. Those two guys, they're both happy where they're at, but we're just going to have to move them around here in a second. Now, with the variables of x, I have the same base and I'm multiplying. So what do I do to the exponents? You add them. So it's the same base, and I have to add my exponents. So what's this stuff? Ready? 2 plus 3. Well, 2 plus 3 would be 5, but what's 2 plus 1? 3. So now I have 5x cubed. Now here's where it gets interesting. I know in the rules, if you will, it says that you take m divided, or subtract n, top divided by bottom. I don't always like that because sometimes if you do that, don't you get a negative exponent then?
And then you two go to the bottom.
Correct, but one way to alleviate that issue, who wins in a game of war? A 3 or a 1?
3. A 6.
Very good. What's 3 minus 1?
2.
So does that 2y squared go to the top or the bottom?
5.
It's a little bit different variation of what they're writing about here when you have m over n. It's just a little bit easier. Whenever you're dividing variables like that, think of the game of war. What exponent's bigger? And that's who's going to win the fight. That's where the exponent's going to win. And you're done. Nothing else you can do. You're just simplifying. Yes, sir?
If they're the same.
Well, if they're the same, well then if they're the same, then you'd have something like this. What's x squared divided by x squared?
0.
1.
Oh. Yeah.
And they just go away. All right, very good. Because then you get x 2 minus 2, which is 0. What's anything to the 0 power? 1. All right, and you've done that before. They just drop out when you're simplifying a fraction. Okay. Same idea here with the other one. I have negative 3xy over 9x cubed y to the negative 4th. When we start the problems, always deal with your variables, or excuse me, your numbers first. What's negative 3 over 9? Negative 1/3. So, negative 1/3. X cubed and x. Who wins? All right, so what's 3 minus 1? 2. So the x squared stays down here. Now it's tricky. I have y to the negative 4th and y in the numerator. Where does that negative 4 have to go? Up top. So it becomes y and then y to the 4th. So my final answer then becomes negative 1 y to the what power? 5 over 3x squared. You've all seen this before. It's just been a little bit of time. All right? And it's going to be the negative exponents that you'll mess up from here to there, from time to time. Okay? Let's try a couple more. Oops. Two y cubed over y to the 5th. 2y cubed over y to the 5th. Bless you. 2 over y squared? Everybody agree?
Yeah.
All right. Now I have 4x cubed all to the 4th power. Now, remember, whenever you have junk to the exponent, you have to remember that you're distributing the exponent to both terms. So not only do you have to put 4 to the 4th power, you have to remember that it's x cubed to the 4th power. Your calculator will be able to figure out what 4 to the 4th is. You guys all know where that little caret button is, right? I'm sure by now you guys know where that is. You get 216, I think? 256, thank you. So we get 256 x to the 12th. Because he's 3 times 4 is 12. At least last time I remembered. All right. And so on. What I'd like you to do real quick, and I'm not going to use this whole 5 minutes part of this. I want to look at number 18. Take a second and try 18. Take a second and try 18. Uh, 6x to the 5th, yeah. Yeah. It's 3x quantity squared over 6x to the 5th. Now the 6 isn't being raised to the 5th, though. Just the x. I was making sure you weren't trying to do 6 to the 5th, that's all. All right. Now, with any luck, did you get that?
Yes.
Good. All right. Like I said, exponent rules, these are things you guys have all seen. It's just going to take a second or two to knock the cobwebs out of your brain. Okay? All right. Well, don't literally knock the cobwebs out unless they're really nice. Let's try something new. In my mind, it sounded like it was going to be a lot funnier. Anyway, 6.2. In 6.2, what we do is I'm going to introduce you guys into how you graph polynomials. But remember, we all have this nice yellow brick on our counter or on our desk here. So the graphing of polynomials is going to be relatively simple to start out with because we're going to be able to use the great old button that says, correct. We're going to use y equals, but when we use y equals, we're going to start looking at tables, and we're going to start watching what is occurring to numbers as things are changing directions and all that. So first of all, I want to describe to you guys exactly what do they mean when you see a polynomial. What does the word poly mean? You remember? Many. Nomial? Sure, many numbers. Sounds good. So when you're dealing with polynomials, and all I want you guys to think about here is a polynomial is a function that's written in the form of a descending order. Starts with the x to the 4th, x cubed, x squared, and so on. Don't worry about how all these things are going. But I want you to think of what this looks like. X to the 4th plus 2x cubed minus 4x plus 2. See how it's written going in the descending order via exponents? None of my exponents are negative, and none of my exponents are fractional. Ooh, fractional exponents, those sound scary. I wouldn't. We will have fractional exponents. That'll be chapter 7. And you've already dealt with fractional exponents. What's a square root? It's a 1/2 exponent. 9 to the 1/2, you put that in your calculator, is 3. A square root is a fractional exponent. You've done it. Okay? So what I want you guys to think of is when we're working with polynomials, we're working with values that are written in a descending order. All the exponents are positive, and they are all non-fractional. One thing you will see, though, is that you could have something like this. Still a descending order, correct? What happens, though, is that I'm just missing the x to the 4th degree, x to the 3rd degree, and the x value. If you had to write that out in what they would call the standard form, you would write it as x to the 5th plus 0 x to the 4th plus 0 x cubed minus 3x squared plus 0x plus 2. What those zeros are doing, they're creating what are called placeholders. And you're going to see that when we use that, what I was calling you guys here a second ago, that synthetic substitution. We need to remember about these things called placeholders. This is still a polynomial, x to the 5th minus 3x squared plus 2. It's just, they're not writing out the values that aren't there. Does that make sense?
Yep.
So just, I don't want you to get hung up the idea that you have to see every single exponent. You could have a 0 value for one of those coefficients. All right. When we talk about, like I said, when we talk about the graph, I think it's what was the next. No, it's not. Speaking of synthetic, let's talk about direct substitution. Direct substitution is something you guys already know how to do. What does that mean, you think? Yeah, you substitute in the 3. If you're using what's called direct substitution to find this f of 3, what you're doing is you're taking f of 3 is going to equal 2, 3 to the 4th minus 8, 3 squared plus 5 times 3 minus 7. That's called direct substitution. Plug and chug. It's what you guys have all grown up being able to do in math. Substitute in and go. What's that? And when you're dealing with what's called synthetic substitution, there's another way. I think some of you guys were already typing away on this one. What did you get? Was it 98? 93, I think? I don't remember. 3 to the 4th is 81. 81 times 2 is 162. 9 minus 72 plus 15 minus 7. 98? Right. That's a lot of buttons to press, isn't it?
Nope.
Yeah, you did something wrong.
You can always count on having a fun day when you spend it with the people you love.
I don't know. I was just trying to have a little bit of fun. Barney!
Oh, God. He scares me.
He's dying. Bless you. It's okay, Wes. You're going to be all right, Mr. West. You're going to be all right. Breathe. Probably. Now, at least twice. Here's a thing called synthetic substitution. Instead of using direct substitution when you're dealing with polynomials, you can use something called synthetic. Now, synthetic substitution is going to look weird to start with. You're going to start to go, why would I want to do it this way? It takes too long. Well, after you get the idea of how you're setting it up, synthetic just flies right through. Also, later on in this chapter, when we use synthetic division again, it's going to allow you to find the zeros of polynomial functions. And what are zeros again in polynomials? Where it crosses what axis? Where it crosses the x-axis. So synthetic division allows you to do a lot of stuff real fast. So this was the old-fashioned way. We just did that, plug and chug. We got 98, I believe, right? Now, like I said, synthetic is easier and quicker. Here's what we do. In order to set up synthetic substitution, what you do is you take the coefficients of your polynomial. Now I'm using the exact same polynomial here. That 2x to the 4th minus 8x squared plus 5x minus 7. Notice how I put a 0 in for the x cubed. I used the 0 as a placeholder. So this was my 2x to the 4th plus 0x cubed minus 8x squared plus 5x minus 7. See, I'm just plucking the coefficients right out, keeping the signs with them. On the outside, I put the 3. Now, you guys are used to using division with the upward bar over it and going in and going through. Well, synthetic division looks completely different. You write it like this. You're basically creating rotated L, let's say that.
How far down should
You're basically going to use one line of numbers below that. Okay? Now, here's how you start this. The first thing you do in synthetic division is you drop the first number. That's why I pointed my arrow down. I dropped the 2 here. Move this up a little so you all can see this better. What's 3 times 2? Put the 6 here. What's 0 plus 6? What's 3 times 6? What's negative 8 plus 18?
30.
What's 3 times 10?
25.
What's 30 plus 5? What's 3 times 35? 105.
No, I was doing the next one.
What's negative 7 and 105? It's mathemagical.
Say the Marty thing again.
No. Where did the 30 come from? 3 times 10. What I'm doing here is I take this number and I multiply to all of these, and then I add coming down. Mr. Mack. Yeah. How far up you gotta go? Okay. Remember, whenever you're using synthetic substitution, it's going to say, what is f of 2 in the following polynomial? You pluck out all the coefficients, you write it up, drop the first term, multiply, add, multiply, add, multiply, add. Last value is your answer.
But you need the placeholder.
You need the placeholders. That's the key. You got to have placeholders. Okay?
And you just don't multiply the last number.
Correct. Because that's your solution. The last value is your answer when you substitute in 3. All right? As we get further in this chapter, if this number is a 0, that means this was a 0 of the function. And we'll get to that. Okay? Let me show you another example. Can I go to another screen?
Yeah, this is
All
0.
right.
How do you get the next one?
He's always having a snack, so I've got to tell him to throw stuff away.
What was it?
Okay.
Oh, okay.
Wait, I was going to say. All right. Same idea. F of x equals x to the 4th minus 2x plus 7. And I want to use synthetic substitution when x equals 2. Now, granted, I understand that this is only a 3-term polynomial. You're using a value of 2. You could probably do this in your head. But it's an easy one to show you, again, how the process works. We start out by making the little upside down, pluck out all of your coefficients within the descending order. I have an x to the 4th, so that first term is a 1. I do not have an x cubed, and I do not have an x squared, so what are the coefficients? 0 and 0, very good. What's the next coefficient? And then? And what do I put out on the left? 2. Once again, as we go through these, you take the first value, you drop it. What's 2 times 1? 2 times 1 is 2, you write it here. What's 0 plus 2? What's 2 times 2?
4.
Put it here. What's 0 plus 4?
4.
What's 2 times 4?
8.
What's negative 2 and 8?
6.
2 times 6.
12.
And there's your answer.
How do you get the zeros?
Remember the placeholders. Since there is no, this is my x
On the
cubed,
x's.
x cubed, x squared, this is the x, and this is my constant. All right? That's what I'm writing it through. Yes, sir?
Oh.
Those guys have the class, it's period 8, 9. That means they have the 10th hour lunch, which means their lunch is at like 1 o'clock in the afternoon. They've been here all day, and I could only imagine, if I didn't eat for like 8 hours straight, I'd want to kill somebody. So I give them the benefit of the doubt if they have a granola bar or an apple or something like that, I'm not going to eat out. Does that make sense? Synthetic substitution is an incredibly efficient, simplistic way to find values. All right? I think I have one more. All right, we'll do another one. I gotta get another one up here. What chapter is this? 7? 6. Getting ahead of myself. Synthetic substitution again. With that, 6x cubed minus 2x squared plus 5x plus 2. And I want to synthetically substitute in 2. So when I look at this, do I need to worry about any placeholders?
No.
No. All right, I'll give you guys a second. Go ahead and write it out, and I'll check it with you here in a second. Told you he's efficient. He's simplistic, isn't it? People first see this and they all go, and then all of a sudden it's like, it's adding together, adding and multiplying. Yay. Yeah. Ready?
So if there's no, if there's like, like for 5x, if there was no 5, it's actually put 0, original 1.
If it was just plus x, then what's the coefficient? It'd be 1.
So why'd you put 0s up in the last one?
There was no x cubed, there was no x squared.
Oh.
I want to go in a full descending order
Alright.
with all my with all of this in there.
Anytime there's no number value.
I'm sorry, I'm sorry.
Anytime there's no number value, it's just one.
Yeah, because that's the coefficient. And it could be a negative one. If it was minus x, then it'd be negative 1. If it was minus x squared, it'd be negative 1. Just remember those signs there. So drop the 6, get 12, get a 10, get a 20, get a 25, get a 50, get a 52.
Yep.
Isn't that awesome? It's pretty cool, isn't it? Very simple. Okay? All right, let's talk about graphs then. Graphs are fun. I'm going to introduce you guys to what's called end behavior. End behavior is basically what's happening at the ends of a graph. Well, what direction is it going?
Way.
I'm glad you say upwards. So here's what I'm going to introduce you guys to here. Whenever you're dealing with end behavior, you're dealing with x's and y's. Okay? Your x value generates the y value. Do you agree? So x generates y, or x generates f of x. So as x is getting larger in this graph, so as x is approaching positive infinity, what is the y value approaching in this graph? Careful. As x is approaching positive infinity, y is also approaching positive infinity. So, what you're looking at here are the tails of your graphs. What is happening as x approaches, this arrow implies the word approach. As x is approaching positive infinity, the graph is approaching positive infinity. As negative x is approaching, I should say, it should be just regular x. I don't know why I wrote negative. As x is approaching negative infinity, as it's going this direction, where is y pointing? It's also going to positive infinity. It's going to positive infinity. So what happens here in this instance, I would write x approaches positive infinity, then y approaches positive infinity. Now your book is going to, instead of writing the letter y, they write f of x. Remember, we've said this, I think we've said this before. F of x and y are kind of one and the same. Yes, sir?
I still don't kind of understand how to do like the whole L equation from before.
We'll do some more here in a little bit. I want to get through this part here real quick.
Like, how does-
Same idea. As x is approaching negative infinity, remember, as x is getting smaller and smaller and smaller, it's going this way. In this example, f of x is also approaching positive infinity. See how the graph is pointing upward? That's all it means.
Oh, so they went those that way.
Yeah. That's all it is. Depending upon what the depending upon what the graph looks like, the y values are what's going to change. You always start with x is going to positive infinity as x is getting bigger and bigger and bigger, and as x is getting smaller and smaller and smaller. You're looking at the tails. The tails are what direction is it pointing? It's pointing up, it's going to positive infinity. It's pointing down, it's going to negative infinity. One can be going one direction, the other one can be going the other. It just depends on the function itself. Those are like the dance moves.
So that kind of gets positive.
Correct. This is, if you think about it, this is an x squared function. As x is, even if x is a negative value, when you square it, you get a positive value. So it's always moving upward. Okay. Exactly. Very good. And we'll talk more and more about that. Now, here's what I want you to do. Take your calculators out.
Was there a button that must have stood?
Y equals. That's why I kept saying f of x and y equals are synonymous with one another. And I want to look at the function f of x equals negative x to the fifth minus 3x cubed plus 2. And all you want to do is look at the graph. I don't care about the table or anything like that right now. I want to know what's going on at the ends.
Oh, I got it.
I want to look at the end behavior, the tails.
I got it,
Then you typed in something wrong. You might have used a minus sign for in front of the x to the fifth.
Negative x. Oh, okay, yeah, use the minus instead of negative.
Got it?
What are we supposed to do? There we go.
Did you get something that looked like that?
I don't know where it's
Yeah, because I don't want you to try to do this by hand. Use your calculator. Your calculator's got this great viewing screen that allows you to see what in the world is going on. So, as x is getting larger and larger and larger, what's happening to the y values? Bless you. So that means, are they getting smaller or larger? So if they're getting smaller and smaller, what value are they approaching? Negative infinity. So in this example, as x is getting larger and larger and larger, y is getting smaller and smaller. So it's approaching negative infinity. Same thing with the other direction. As x is getting smaller and smaller and smaller, what is y approaching? It's going the other way. It's going to positive infinity. Your calculator will be able to tell you that. All you need to be able to remember is how to start it. X gets bigger, x gets smaller. What's happening to y? And instead of writing the letter y, write f of x, and you're going to be fine. Okay? Well, let's talk about this one. In this graph, there's a kind of a W, isn't it? But in this case, does that make any difference about the ends of the graph?
No.
It doesn't. It has no bearing upon the end of the graph. So as x is getting larger and larger and larger, what's happening to the y's? So it's going to positive infinity. Same thing, as x is getting smaller and smaller and smaller, what's happening to the y's? Positive infinity again. So remember, you're not really so concerned about what all of these things are, what's occurring here, when they're just asking about the ends. Remember, end behavior, you want to think about it as the tail. These are the tails of the graph. What's happening at the tail end? Who cares about the middle? When they're just asking about the ends. Does that make sense? Now, What if they ask you about what's going on in the middle? What are you going to do?
Scratch it.
Scratch your head? Hop on one foot? If you put this function in your calculator, you don't drop your calculator. Put that in for a second, would you? X to the fourth minus 4x squared plus x. And you should get that W-looking thing. I'm glad you humored yourself. Nothing. Do you guys all get that W-looking graph? Yeah. All right. So let's say, for example, we wanted to take this, and I wanted to a rough sketch. How in the world would I rough sketch this?
Just wing it.
No. Is there happen to be a button on your calculator to allow you to find some ordered pairs? Yeah, there is, isn't there? Where is that button? The table button. All right, so if I wanted to do that, I'd be able to use my table function, and I could plot some points. Now, as we get into this, it was kind of like this, right? Ish, whatever. I know that it went through the origin at 0, 0, because if I substitute in 0, I'm going to get 0. But what happens now is that you have two dips in there, right? Now, when we talked about just a regular parabola, we talked about it having a minimum or having a maximum. This one appears as if there are two minimums. But it depends on which one you're looking at then, right? Now, this comes into a new term. Local minimum or local maximum. Local minimum or local maximum basically has the same definition. One of them, one of them's up like a cup, the other one's down like a frown. When you're talking about a local minimum, I'm talking about a minimum in this region. I'm just looking at, in this area, what's the minimum value? Can your calculator find that?
Yes.
Exactly. Now, this problem would have how many local minimums? Two of them. So could I use my second calculate minimum function on my calculator to find this low point, and then do it again over here within the boundaries of that and find that local minimum? That's what you're looking to be able to do. There will be times that you'll have two local minimums. You might have a local maximum. You might have a local maximum and a local minimum for those style problems that go like that. You'll have one of each. Okay? What I'm explaining to you is just when you start to see these new definitions and terms, that's what they're looking for. Does that make sense? Graphing of polynomials, for the most part for us, is going to be relatively simple because we have a table function on our calculator. We're going to be able to do that. It's the new term of that local minimum or a local maximum, but your calculator does that with second calculating what's minimum is 3, I think, and then I'll scroll through there. Okay? Not horrible, is it? I don't think I had any other ones. This discussion, we just did that, and behavior, blah, blah, blah. Okay. Do those. All right.
How are you supposed to set up the whole L thing?
All right, when you do the L thing again, remember, all you're doing is you have a Z, you have a fourth degree, you have 0 x to the third, you have 0x squared, you have a negative 2x, and a positive 7. What you're doing is you're taking your coefficients. So it's a 1, 0, 0, negative 2, and a 7. And then you take your 2 and now drop it. 2 times 1, add 2 times 2, add 2 times 4, add 2 times 6, add 2 times.
So basically what you do is sort of like simplify it or it gets to the square?
No, you're not simplifying anything. You're just putting in you're putting it in that placeholder. That's all it is. You got to put a placeholder in to make it work.
We're doing something.
Just a reminder, I won't be here in the afternoon, so I'm sorry I won't be around for Flex. But if you need a Flex Pass, Mr. Judkins said he'll be able to help you guys out if you had a question. Talk to him really, really fast. He'll be all right. Tomorrow's lesson is very, very easy. You will be happy. Oh, no. Oh, okay. Whew. I thought I didn't press start again.